All right. Yeah, so Ted will be out today. Um, so we'll see how this goes. We're talking about vase mode, which is like his baby. Like he loves vase mode. Um, so I hope that I'm a faithful interlocutor for describing the vision of vase mode and how that works here. Let me switch to a repo here and get everything situated. Okay. Yeah, I noticed some of you are starting to make progress on the knock compiler from the last homework. How's that feel?
I can actually like read knock now a little bit. Wasn't able to do that before. When you were like going over it, Neil, in the first lecture, I was like, what
Mhm.
is going on? But it's a little easier now.
Yeah, it really helps to muck around either on paper um, or to write a compiler, and then you can actually see, okay, this is sort of like how things resolve. Because it's weird because you have to like scan it left to right, and then you have to resolve it right to left to make these
It's
things
very
work.
weird to read it the first time, but once you start doing a couple, you kind of get the hang of it.
Yeah. So we are going to jump up to the next level from knock now. And what we're really interested in today is how do we get from Hoon to knock? Knock is what we're actually running. We decided that we're not going to worry about knock bytecode because that's particular to the runtime implementation that you're actually on. And it turns out in practice, unless you're doing something like what Matt was doing with the SIGGAR changes and everything, or excuse me, SIGLESS changes, it doesn't matter. You don't need to touch knock bytecode. So the next place to go then is Hoon. Like how do we actually build Hoon? What does it mean to process and parse as Hoon? We'll get a sense for like why Hoon. Hoon is sometimes described as like an assembly language or a macro or something like that. Um, and it really is a lot like a macro with some type checking and other things that aren't present in knock. So the place that we're going to start first is what's called vase mode. A few of you have perhaps worked with vase mode before, depending on what you're doing, but vase mode is essentially a way of sort of cracking open nouns and working on raw nouns while carrying around type information as you work with things. And it's extremely powerful. It lets you do things like I can grab we'll see how to do this later on. I can grab a gate and I can pull the sample out and say, well, like what's the sample of my gate, right? Like in regular Hoon, this is largely inaccessible to you to actually say like, okay, like what is my sample? How would I look at that? How would I grab that? So if we go back to like what a vase is well, you tell me what's a vase? You've run into vases.
Base is a pair of a type and a noun that
Type
fits
and a
the type
noun.
that
Yeah.
should fit the type.
Yep. Now we use these when we're passing things around in Gall. And we use them in a few other places too. The idea is that at least from the user space perspective, a vase is useful when you want to transmit information uh, about a noun that can also be treated as an executable value. So there's a sense in which, because knock is homoiconic and code and data have the same representation, when someone hands you a noun, you don't know, am I supposed to interpret this as a value? Am I supposed to interpret this as data and actually execute it? Am I supposed to like slam it against some other, slam it against my current subject, slam it against my current subject and see what happens and so forth? So the type information in this vase is what lets us know basically how do we treat this noun when we put this together. And if you think about Dojo, right? So in Dojo, I just ran cold Dojo wipe so I could clear my Dojo state. But in Dojo all the time, we're doing things like defining temporary values. So I'm giving it an input, and then I'm asking Hoon to parse this and put it together so that it's present in the subject. And so, you know, when I did dot a moment ago, my subject contained my bowl and then the Hoon standard library all the way back up through the stacks that exist there. If I do dot now, you can see that value 1 has been added to my subject. And it turns out that basically thinking about the vase algebra, working with things in vase mode, is the way that we compose values together when we're going to evaluate them or when we are going to put them into the subject the way that we have here. Now, when we say type and noun, you know, so let's just take a, you know, so dot 1 2. So this is a single precision floating point pat RS. We're getting two quantities here. So the second one of these quantities, this Q value, is more legible if I pat UX, put it this way, and you can see, okay, this has a bitwise structure that adheres to IEEE 754 description of what is expected in a floating point value, in a single precision floating point value. So it's 32 bits wide, etc. The other part, the pretty printer tends to eat this, and it's often harder for us to see what's actually going on with this because the pretty printer will frustrate our efforts to look inside of it. So we need to decompose it to sort of say, like, okay, what is type? What is type doing for us? So if I just look at the head, if I do the type sphere, then I still get this #T faz pat RS. Anywhere that the pretty printer puts a hex, what it's referring to is what in user space colloquially we are calling type of type. Means that it is picking up that it's a pat RS here, but it's doing it some roundabout way. Because if I type pat RS by itself, what do I get? Right, like pat RS is a gate, and so it is giving me information about there's a battery, there's a sample, there's a context with the second information here. So I can do things like, you know, ask what's the, I guess, you know, if I ask for the actual sample, it gives me the bunt of the sample. If I ask for the context, it processes it into whatever is visible in my current subject and so forth. But if I do pat RS by itself, this is already resolved to a gate. And so what we're running into here with the type of type information is that there's an inner way of thinking about what is taking place if I am talking about the type of a value. So if I go inside, then I can see that there's a head tag atom, there's a tail that's a sen RS, and then a sig. So I can actually say that what I have here is sen atom, sen RS, sig. And if I ask Hoon to identify this as type, then it reduces back to the same value that was on the outside there. Hoon uses the word type a few different ways casually. So when we first introduced type in Hoon School, what we're basically talking about is it an atom or a cell? We're talking about a mold. And of course, at this point, you know that a mold is a core. It should be idempotent. So if you give it a particular value that's already matching the type, then it'll give you the same value back. Although I think the mold system was slightly changed in December, and I don't know that that guarantee is always there anymore. It's changed the value of MICMIC as well because of that. We also use it to mean mark, right? In the same sense that we'd say something like a file type or a MIME type. And when we talk about a mark, we're talking about not only something that has like a noun representation, but it has rules that facilitate converting between these nouns, so that you always have a road from one place to another. And what we're going to be talking about with type here now is sorry, I moved my Zoom stuff around. Okay, there we go. what we're talking about type here is there's actually a value type inside of Hoon.Hoon. If I do type here, okay, yeah, I get this thing back. Let's go into Hoon.Hoon and take a look at it here. So that's if you have the Urbit repo, it's in package arvo sys Hoon.Hoon. We're going to search lessbook gap type, and we'll have the long statement here of several lines. And I will also copy this over to the working file so we can see it there. All right. So in Hoon, what we're going to say with Hoon is it's a definition, or excuse me, with type, is it's a definition within Hoon. It's a way of specifying a set of nouns. So at some level, we could say, something's an atom, and this describes the set of all atoms, or we could say it's a cell, the set of all cells. When we talk about type and we specify that we're talking about lessbook type, the formal type in Hoon, we're not really using type in the same way that we were casually using type when we were talking about moles and so forth. What we mean is we actually have some sort of, and you'll notice that it's an internally recursive definition. We have this formal tree-based definition of what is a type, and it's a description of exactly like what is the thing that I have. So notably, noun is the superset of all nouns. And that can resolve to a noun or a void. Void will not occur in practice. I think maybe there's something you could do with zap or something to get void, but in general, void is there because it completes the type system to have an empty value in the set, right? You can have an empty set, but it won't be generated by any actual Hoon code. Or you can have the set of all atoms, or the set of all cells, or a description of something as a core. So this will use this as a type. This has a coil. Coil is interesting. Coil is a set of variance information, context, and chapters. So if you want to know where wetness, dryness is specified, if you want to know if it is a gold, iron, lead, zinc core, then that's specified in this coil. So this gives you the additional type variance information is manually specified here. A face gives you it calls it a namespace here, but it's basically the same set as nouns, but with faces, with labels attached to things. There's forks, there's hints, there's holds. Hold is one we're going to run into quite a bit. So this is a lazy evaluation, and it's why the compiler runs into troubles with lists at runtime. So, obviously, if you've done Hoon for any amount of time, you've run into the case where you either have to assert using whatsig that a list is not null in order to use the I face and the T face within a list, or you may have to go back the other way and assert that a list is a list, restore the as yet unknown information for something like snag or snap to work. You run into the TMI problem, the too much information problem that the compiler can have. So, and then a fork means that we haven't made a decision between possible elements in a union yet, right? That we're containing a set of things. And it turns up in other cases where, perhaps we have a type that can allow different named tuples within it, something like that. Then you can't access them through their faces until you've resolved that fork that you've done. Typically an assertion, a whatgar, or maybe a micmic would be a way of resolving that. Now, let's go ahead and actually just poke around inside of list and see how this behaves. So let's do list. Actually, let's go even one simpler. Okay. So let's call this A, sig 1, 2, 3. All right, so if I type spear A, then I get that this is a tuple literal with 3 elements and it's null terminated. So, 4 elements if you count the null termination. And that is the information that the system simply has about this. So if I were to access the head of this type of type, and I'll show you a way around that in a minute, that'll make it easier for us. But if I were to access the head of it, what kind of type would be the head tag that would show up there?
Cell.
Should be cell. Yep. So that'll be cell, and then if we look to the right of it, it'll give us probably it's a collection of cells. I think a cell. Oh, you run into this sometimes when you try and show something that has type inside of it, which means it hasn't resolved some of the things to the right. It'll just crash on failed to process input. What's happening in that case is it's attempting to print the entire standard library because type contains basically all that information inside of it. So you don't want to end up in that situation. You run into that with mic too, like where you actually can't mic things. What we'll do here, a way of getting around that to show the actual whole value is we can actually coerce it to one of the particular values here. Yeah, there we go. So that'll unpack that for us. And let me give you that here. All right, so that lets you assert that if I know the thing I have is head tagged with cell and then contains type. If I know it matches everything, then I can put it together that way. But you'll notice too, what am I getting? I'm getting a cell, and then there's types within it, and so I have this whole tree of values that I could probably cast to a noun. No, that's doing the whole. Oh, that's sorry. That's the head. Yeah. So there we go. We're getting the cell. We're getting the UD label. Don't know what 110 might be the sig literal, perhaps. No, that has to be the 0. I don't know what that is actually. Anyway, we can look at it the hard way, or we have to do weird things like do this coercion because the pretty printer is so eager that we can't get around it directly. Okay, another one. Okay, so that's what's happening when it looks at A, because A was a null terminated tuple, had no other information about it. Now, it's been frustrating to sometimes, if I want to snag 2 out of 1, 2, 3, this fails because snag actually needs to know that what it has is a list. It's not enough for it to structurally be a list. It actually has to carry the type information. And this is what type is doing under the hood that's not apparent when you are just working with, totally user space Hoon, what's going on with this. So now let's define B as a list pat of A. All right, so B and A, the pretty printer is picking up that they're slightly different, giving them a slightly different form here. But what we're getting now is if I were to grab the head. Yeah, so okay, let me just type spirit. If we type spirit, then we get that it's an iterator. So it's picking up that it's some sort of internally recursive type. If I grab the head of that, then I can see that it is a hold. It's a lazy evaluation. And this is where the trouble comes from. Because the list, as I'm talking about it as a list, has not yet actually been resolved into, the type has not been resolved into a particular list. And so it doesn't know if things like the I face and the T face exist. And this is why, because it's not a cell type with values following it. It is now a hold type with other things going on from it. Now, what I should be able to do with this is I should be able to mic this. Let's do hold type, see if we can get that one to behave. You may want to wait a second to see if this resolves before you actually run that.
I recall maybe like if you like make a new type and then make it just like add like a new case and then cast it to that, so like upcast. I recall that doing the job.
There's about 3 tricks that I have written down that do this in various ways. I think micking might have been the mistake here. Yeah, it's caught on that. I've got another version of it where I do it over union of core and hold, and that one was behaving better, I think. No, it's still sitting on it. Let's try cold dojo bar wipe, make sure there's nothing in our state. No, I guess these never resolved because they never, yeah, let's not even mick. Let's try. I know how to do it. Okay. I'm gonna do it with a with an assertion. Should be able to do this on a core or a hold of the head of, actually, I'm gonna want to Tizless this. We'll call this B type, and this will be Sapgar B, and then I'm going to assert that the head of B type is that, and then output B type. There we go. Okay, there we go. That's a little bit more compact. All right. All right. Can you see what I did there to make that one work? So I captured the value because if I evaluated this twice, if I took the head of it and then I took it again, it wasn't going to stick to the same quantity. I needed to attach a particular referent to it rather than recalculate it. And then I asserted that it was either a core or a hold, which then reified the information enough that I could actually print it here. So it's a hold where its first type is probably something about list. And then the rest of it is, what do these look like? Has anyone run into these short codes before? Tizless, what call?
I mean, it looks like a parsed syntax tree.
Yeah, so this is a Hoon AST, abstract syntax tree, that's been parsed out here. So basically what it's saying is I haven't resolved the rest of what's going on inside of this statement here with all these names and values, because I'm still holding on the fact that I don't have information about what this thing is that I'm working with. The other way we can show this in brief, actually, and this might be a good one to use in many cases, is what should do this. Well, maybe that was too big of one. It'll work for short ones like atoms and things. Yeah, I think we're just running into it's hitting the yeah. So if I what sig 1 2 3, yeah. So there I get my cell atom cell null or atom null set up there. So what we'll just dump this information if it's short enough to be printable, which it is not always.
A quick question, Neil.
Yep.
Why did you need to, when you were casting earlier, the like B type with the core and hold?
Yep.
Why do you need to, since it's a hold, why do you need to also ask if it's a core? Like, what did
I probably don't. I think that was just me covering bases. Yeah.
Okay.
So it'd work either way.
Okay, that makes sense. All right, thank you.
There are others that will resolve to cores. One example I have here is this. And so this is actually taking decrement and resolving it to quite a long core in this case, with various values in it. We're going to talk about repo and some of these others in a little bit later on. The problem, so we actually have an interesting problem, which is that if we ask for the head of a gate in our current subject, it always resolves to a hold and not to a core. We have to do something to actualize it, to get it to evaluate past that lazy evaluation. Why do you think that might be? Like, why is dec and add and everything a hold instead of a core?
They all come from like I'm pretty sure all holds in the entire compiler come from fire inside of ut, which is basically what's done when you're like evaluating an arm with sentences as opposed to a face. And what that basically does is just like check that like the change type in the core kind of like matches right, and then creates a hold of like the core, and then like the hoon of the arm. And so when you do dec, it's finding the arm and like the core of like the standard library, and that's where that hold's coming from.
Yep. Yeah, and you can think of it as being analogous to the way in which we can talk about an arm, but like we have to go get the core. Like we have this gate building gate pattern. This is related to that, where that you have this valid wing lookup, but you actually have to go retrieve the thing at that address, make a change to its sample, and then at that point, essentially, you have a core, and then you would actually, slam the result, slam that gate to get the value out of it. So Hoon does lazy eval in these cases to get ahead of those problems. Now, so that's Hoon type. So whenever we talk about Hoon type, this is what we're going to mean in the context of Core Academy. When we're going to talk about, we're going to use phrases like the type of the subject, for instance. This is what we mean here. So we can talk about our whole subject having a type, and essentially this means that we actually have a logical description of what are the quantities in my subject and how they relate to each other. Actually, now I'm curious what this won't break everything. What is the top level of my current subject? Yeah, so my current subject is a cell, and the left-hand side of that cell is probably well, it's probably the whole Hoon standard library. Actually, I was going to say it's 139, but I probably picked up everything when I did that, so I won't run that. We'll let that die. Killed Hoon. All right. So now that we have type, now we can talk about we have a vase and we have a type and a vase. This is what we mean when we say we have a type and a vase. So the most common way to get a vase is to use Zapgar, and this is what you've done in Gall agents and most of the things that you've ever worked with. You have some value, you have whatever it is. Maybe it's validated through a mark, or the way that you do with SIR files, like actions and updates and everything. Maybe not. You get this value. You can also manually construct a vase, and you'll see this more in the kernel, where for some reason, people might be putting things together here. I think I just need a 4 there. There's actually that last one is actually a unit, and so you can play some interesting games where you can create a vase that doesn't follow the rules, right? So here I just made a vase where that last value is basically dependent on whether or not this thing is a constant.
Why you guys just merge Andy's branch so that his change is independent of mine?
Is that a
And
question?
then that way, like, we can at least get the
Maybe not. Okay. So what I've done here is I've created an evil vase by specifying something about the type that doesn't actually match the value. And so this will break at some point. So you have to be careful if you're actually doing manual construction of vases rather than letting Zapgar do it for you. To start off with what we're going to be doing with vase mode is the big picture is we're going to be able to use the type and the value. We're going to be able to compose and decompose these. So we're going to be able to take two vases and combine their types and combine their values in some way that lets us, do an evaluation. A lot of compilation, for instance, is going to look this way. This is what Dojo is doing when we type information. When I give it some new input, like if I just give it a number like this, it's not. I mean, it may trivially be doing vase mode, but it's not doing vase mode. It's not composing vases to actually make this work. If I'm throwing in some value like this to C notation, now I've modified my subject, and the way that subject got modified, there's the C. The way that the subject got modified was it took the type and the value of the previous subject and the type and the value of this new pair of 5,000, and it composed them together. And so there's this isn't actually going to be an atom. This is going to be a face. So I should be able to just say, may have to say it some weird way like this to get it to say face. Yeah. So I have to specify that on top of it if I want to do that. And if I could get the address of this as a face rather than as the value of the face inside my subject, which I guess might just be. Yeah, so I actually should be able to just say Tisgar. Yeah, so I can get the face that way. They call this a programming language. Look at that statement. All right. So an evil vase means that we have a mismatch. And it can be trivial to do if you're building them manually, but obviously you don't want to do them. So we also want to be able to eliminate vases. So we're going to call it elimination, but basically this is going from a vase back to a statically typed value. And we have three ways to do this. So the first one is to Zapgal it. And you end up having to provide it a vase and a type. It sort of doesn't operate directly on the vase. Like you still have to provide that external type information for that to work. So we're collapsed. I mean, the way that this used to be described in the docs was something like it was like elevated dynamic value back into a static context, something like this. But this is what this is doing. Is it's taking a vase where we may or may not have information and putting it back into something. So let me actually try this with Zapgar with that evil vase that I created a minute ago. Yeah, so it actually is going back in as 4, and it's ignoring that constant information entirely. Yeah, so that's a bad one. If Zapgal doesn't work, we're going to do Micmic. Micmic takes a type and a value and coerces them. And in its current form is basically equivalent to just doing a mold operation, which is the third way, to just do a straightforward mold on the value. Now, what I'm curious about is it seems like there should be a way. Yeah, Micmic doesn't want to let me use type of type. Zapgal might. I think that this will probably fail because it's not actually the type of type is not actually a mold. Yeah, it's not going to let me do it that way. Anyway, so you have the vase information, but the vase information doesn't actually translate to like an operable type rather than operable value. You always have to have that information available when you build this thing. So we know how to create vases, we know how to eliminate vases. Our vase algebra then is going to be how do we combine these things? And Ted calls this the slap slop algebra. And the short version is that slap in vases Hoon or shares two vases together. Excuse me, no. That's the share is slop. All right, so what we're going to do is we're going to be able to take some value. We're going to be able to take some parsed Hoon expression and turn it into like run it essentially. One example. Let me give you an example of this first. And then you see like sort of what it's doing here. All right, so what I've done, we'll see what ream dot does. All right. So ream dot refers to basically my current value, my current subject. So I'm presenting it with a subject as a vase. So a type and a value as a subject. So, type of subject, this kind of terminology. And then I'm running a Hoon AST against that value. We're going to come back to Hoon ASTs in a little bit when we talk about compilation. So it runs a Hoon against a vase, and then it produces a vase of the result. This is going to be the operation that we're going to use. The actual contents of slap looks like this. Or it takes a vase and a Hoon, it returns a vase. Inside, it's going to run mint ut against the head of the vase, which is the type. With the type of noun, it's going to run that Hoon against it. And then it invases the product type and dot tar, so the actual evaluation of the knock against the subject passed in. This is like kind of messy and complicated. What mint is going to do for us is it's going to produce a knock for us. So we're doing everything in knock at this point, and then if Hoon is smart enough to know how to pull this back out as a vase, then it'll typecast that back up as a vase due to the cat heb here. So gun is the knock that actually gets run when we run the noun in gen against the subject of P. So the mechanics of it we'll get through as we run through some different versions of this. You can think of this as Hoon's dot tar. It's the Hoon equivalent of a raw knock 2, where we're just saying we have a formula and we would like to run that formula against a subject. So the vase is your vase of the subject, and we're going to run the formula against it. So we should be able to do things like refer to C in the current subject. Yeah. So I can also run a vase of my current subject, and then I can run whatever ream gives me, which is that parsed Hoon expression against my current subject and get that value out. This is what Dojo is doing for every input that you have that isn't like a definition or something. So this is why there's Dojo specific syntax like tis, because it's kicking it into a different mode like slop would put that together, which we'll look at in a minute because it'll share two bases. So what slap is doing is every time you type something in Dojo, it's slapping it against the current Dojo subject, which may be a different subject than other parts of the system. It's actually, I mean, I think this is a neat piece here. Now let me give you Yes, I want to paste 2 lines of text. Okay. Let me give you this version here. All right, so when I actually when I run knock with zaptiz here, so I'm just retrieving the values at slot 2 and slot 6 inside of this this tuple. What I end up with has no further information about faces or type information, right? Like knock is a typeless language in that sense. If I were to do the same expression, let's do it as a zapcom, and then you always need a bunted hoon for that. Oh, why are you doing that to me? I think it's because, oh, I'm evaluating against the subject that I just had there, which means I'm actually losing my information. So Zapgar will evaluate a statement against the given subject, and so if you don't have your current subject present, then it'll lose it. So I'll do this, which will be basically equivalent here. All right, and so the Hoon that results from Zapcom has ket tis statements here because we're adding faces to things, and so the face that's added is 1, the face that's added is 2. There's a coulter. This is a lot more complicated than the equivalent knock that comes together, and so this is what Slap knows about these Hoon things, knows how to put them together. And this is why I say that it's like Hoon's knock 2 in a sense. And so there's a lot of we have like a Control L, I guess, clears it. Okay.
Wait, how's that like? It's cons, isn't it?
You mean, well, slop is like cons. What do you mean?
Oh, never mind. Yeah, you're
Okay.
right. You're right. Yeah.
Slap is basically knock 2 in Hoon. It's like Hoon's eval a raw noun. And then slop is like cons 2 vases together, but be aware that the type information and the value information have to sync differently from each other. And it's also very short, like slap. So if we slap, let's do some statements like this. If I slap against some arbitrary subject, then I get the values that are present in that subject. But that subject is all that's visible to the statement that's being reamed on the right-hand time, right? Like this is the way that's getting put together. You can also do things like, yeah, I mean, we can resolve by name. Anyway, all this information gets carried around. This is why slap is nicer than knock 2 from the Hoon perspective, if we're up in the assembly layer language here. All right, so then slop is our cons. It's the way we're going to put 2 vases together. So we're going to get 2 vases, and we're going to make a cell that's the head of each vase and the tail of each vase put together as a vase. So it's smart. It knows about how to put these together. So if I slop some value with some other value, then it knows how to compose these together. And this is like fairly trivial. It will keep track of type information. If I were to do things like let's do a foo tis 4 bar tis 5, and then let me do a bar tis 6 baz tis 7. Yeah, it knows to hang on to these things, and then I can slap against that with a, I guess I need to ream ket bar. Okay, so it considers the first one. I guess if it's doing depth first, then it's hitting that before it goes down and finds the 6. So that makes sense. Okay. Now I'm actually curious, what does ket resolve to? Oh, there's like a, and there's, okay, so there's like an annotate, there's a metadata annotation on the right, that P on the wing, that tells you how many times to skip. Interesting. Okay, so that's actually just gets folded right into the Hoon AST when you skip a match on a wing there. All right. Anyway, with slap and slop, now we can start building higher level operators. And so each value is going to be a vase, and then we're gonna use slap and slop to put these things together. So for instance, here's a diagram of if we were to slap, slop, vase 1, slop vase 2 against slap vase 3 against Hoon 1, quantity against Hoon 2, then we get this kind of diagram here. So we are going to be basically building things in Hoon this way. When we talk about Ford in a few minutes, this is what Ford is doing with FASHEP and FASLAs. It is slapping and slopping together the builds of the other files on the desk, and that's how it gets put together. Here's a longer example. All right, see you, Gary. All right, so what's this one doing? This is actually coming to the same thing, slap V3, H1, slap V2. Yeah, this is the same thing. Okay, so this is the example in Hoon composed together there. So we're actually running foobar baz kooks against these quantities. We're reaming send result at the end, putting all these together. And you can see we end up with a vase here, and yeah, so it has the constant values baked into that. So compilation and execution are going to take place in vase mode ultimately. So for instance, we talk about slamming a gate. All right, so take a gate as vase and arguments, run it. Okay, so if we're thinking about, let's say we want to write a slam, and this will be a homework. So if we can actually solve this right now, that will be helpful for those of you who are paying attention to hear it. All right, so let's say I want to take a gate as a vase, and I have arguments as a vase, and I want to run this. How would we do this? So we have to have some way of putting the, I guess first off, let's see what does the vase of a gate look like? Let's start there. All right, so I just ran this and I got a whole bunch of knock. All right, so I get a type that is, okay, so what's going on with the 1 and the 33 here?
That's a subject. Those are cores in a subject, right?
Okay. What is the subject then? For add. You're right.
It has its own. Sorry.
You're right, but like so what is it?
I know that has like the other cores in the arithmetic arm, right? Like
Mhm.
so like added self will be in here, I'm pretty sure. And right, it's like the parent core. Am I getting this wrong?
Yep. Yeah, you're right. Right. The parent core of an arm is the subject. And since we're in add, we are only seeing the first two cores of Hoon, the innermost core, which is just the type definition, and then the second core, which is the first set of arithmetic arms. All right, so this is all encoded in this. So that's our context. Here's our sample, and all this type information is stored here. And then the actual value that's being provided here. 1.pnw is the pretty printer's way of describing a core. The second part is a hash of the core. I don't know exactly how it's calculated, but it means that there's a core with one arm, which in this case is the fact that there's a label over the core that we're working in. And then all the rest of this value, which is what's actually being run against this type of the subject. So there's a type of a subject, there's the other things inside of it. So if I want to compose those together, let me just call this, I'll call this subject. So if I slop my gate and my args together, then I'm making my args available in my subject with those faces. And then what I want to do is I want to slap the subject, so slap that slop against the Hoon that results the Hoon that results from evaluating the head of that subject tail of that subject. Is that right? Let me double check against the actual. Yeah, here's the actual implementation. I got, let's see. Yeah, so this is how we're actually going to run code when we get code. And so if I were to run this value here, all right, so I have a hold type. I'm going to slam dec against 5. So I'm going to decrement 5, which would result in the value 4. So it's going to be a hold over this other information. So you're going to notice that everything starts with a sig cab and then a rock and everything. This sig cab at the beginning, this is dot chord wrapper around it. So dot chord, it's nice from a documentation standpoint, but it adds a lot of boilerplate on top of the code that we might otherwise see. The meat of what we're interested in is this, which is basically the statement of our actual decrement gate. Like, how is our decrement gate actually built? And it's a hold, so it hasn't been evaluated yet when we do that. So now I can use an elimination mode. If I run this, I can use an elimination mode to get it back out. So let me try. Yeah, so if I slam those values, then I get this. And you can just see this is what it actually results in at that point. So this is code execution in Nock. This is exactly what's happening here. There's some things like slots. Let's see, I guess we're about an hour for base modes, right? And then we'll do about an hour on compilation. That'll be good. Slot is used to decompose vases. So if I give it a vase, did I have a vase that I built a minute ago that was like a good? example of a vase. I guess if I slop all these together, that works. So I'm going to call this, val, and I'm going to paste this whole chunk here for you. There you go in the chat. All right, so that should result in, yeah, so val is that result, and I can actually work with it. So now I can slot to val, and it'll decompose the vase, it'll decompose the right-hand side of that vase. Yeah, I can grab foo out of it, bar out of it, whatever you have. So what slot is doing is it's getting the axis in a vase, but it knows that it has to pull from both the type at that axis and the value at that axis. So you can decompose these things together. Now, the neat thing is we can use this kind of algebra and everything now to do things in vase mode that we can't normally do. So if I actually wanted the type of the sample from a vase for a gate, so let's say I have a gate, if I type add, then I can see that it has this information, but it's sort of not directly accessible to me because actually add is behaving well there. Now I'm curious what oh, it's because we're doing we don't have a vase. All right, so if I have the vase of add, which was all that information that we had a minute ago, then I can do things like examine the type of that, and I can also get is it a hold, is it a cell, what do you have? Let's look at +6 there. All right, so I can see that my actual value is a cell in that case, and I can start to grab these values out. And so I end up with a way of, let's see, I guess if I tislus this, so I pin it in my subject, and then I do an assertion like I was doing before of cell type, and then just, it could be a type or a noun or whatever on hep. Oh, I just want the, there we go. I just wanted the head there. All right. So now I can actually get the type information of the sample by doing this kind of operation. And so now I can ask interesting questions about, if I wanted to do some sort of dynamic programming that was based on the faces that were presented to me in a sample or something. What's a good example of this? So for instance, let's say you wanted to write an agent wrapper that operated on certain cores and needed to be dependent on what was happening inside of the agent, what could be done at different points inside of the agent. Vase mode is what you would have to do to be able to extract that information given a core. And this is assuming that you have the right visibility with variance and everything. Although it is my understanding that Joe has told me that we can actually use vase mode to completely sidestep core variance, opacity, these kinds of things, and you can actually extract information in all sorts of interesting ways using vase mode that are not possible in conventional Hoon by doing that. Unfortunately, I have not delved further into that. Yeah, as Sarpin points out, variance is just a tag on the coil type, which was what we saw on the type up above. Yeah, so if you can decompose the thing, then you can basically sidestep the restrictions that regular Hoon is putting on you with the compiler. All right, so that's vase mode. Vase mode leads us into the compiler stack. Like, how does Hoon begin life as text and end up as interpretable knock? How do we run that way? There's a few different paths we can take. So commonly we can start with a text file containing Hoon code. All right, so we have a .hoon file, and that's going to be processed via the Hoon mark. So maybe we'll want to take a look at the Hoon mark and see what's going on in there. We can also just have a text chord containing Hoon code. We were doing that a moment ago with Ream, for instance, right? We were giving Ream some Hoon expression, and then it was evaluating. It was giving us like you can actually write anything you want in a Ream. Ream doesn't care if what you're. It cares that it parses as valid Hoon. It doesn't care if it knows what anything is in it. There is no foobar baz in my subject. Ream doesn't care. It will produce a Hoon abstract syntax tree that refers to those wings, but then it's going to, when it resolves against the subject, the way we were doing a moment ago with slap and slam, then you'd actually have to figure out, do those exist in my subject type? And then the third way is we're just gonna have a noun interpretable as a Hoon AST, which is a Hoon type. Okay, so we need to go from so our basic life cycle is going to be Hoon code to Hoon AST to knock, and this is actually going to be a Hoon, and this is actually going to be a knock. Some of you were using knock. I'll call this a chord, but it could be something besides a chord. Some of you were using the knock type and ran into some interesting problems because of the recursive nature of that, trying to resolve that. Okay, so there's actually several paths here. Ultimately, they all go through Mint, which we saw a moment ago when we were looking at code. But there's a lot of ways to get there. So ride is one way to do it. Ride is going to accept a pair of type and an atom of text containing Hoon code, so a chord, and it's going to just resolve it for us. So if I write a value, then that should just resolve those two things. So now we know what a type is. So I should be able to give it, I don't know, it's probably, yeah, I think because that atom has to be, the value is text, right, ends up being kind of a weird way to actually run these things. But it is a good demonstration. So the first one we'll look at is ride. All right, here's the actual text of ride. Accepts a type and a text. It's going to return a pair of type and knock. So it's not returning the Hoon AST or anything else. It's returning knock to us. SIGGAR slog. So we talked a little bit about raw hints last time. So SIGGAR, we're just outputting a value that we're parsing here. We're going to ream the text first. So we saw ream. We'll look at ream again, but ream basically takes us from text to a Hoon AST. And then there's a SIGGAL here. What does SIGGAL do? It's another one of these flipped order things. So SIGGAL will resolve after the value after it is. Mint is going to accept a pair of a type and in this case, Hoon AST. And the type that I'm referring to is actually this type here. So any Hoon AST resolves to a noun. Ultimately, right? So I can always call it a noun, even if it's a hold, it's a core, whatever. I can always wrap noun on top of that, and I get the value that I want. And then I've already plugged type into the door, into the UT door that contains Mint. and I run that, and it spits back out to me a pair of type and knock. So that type will be retained and or modified, whatever it needs to be done, and it'll give me the knock back from that as well, as converted knock. Another one is make. Make does it in one step without any commentary, basically. It just reams text. It's going to mint ut of the noun. It doesn't hang on to the type information the same way. So make is weaker in that I can give it any Hoon. But what's going to happen if I give it the name of something? Right. There it has no subject. I mean, like its subject is functionally empty. Like there's no thing there. It's just its subject is the noun that's passed straight into mint. So it dies at that point. But it will give me the knock otherwise. So it does give me a 1 and then a 1, 2, 3 not as my my knock value there. This, if you're still working on the knock processor example, the result of make might be a good way to think about it. One of the things that I like about the Mint builder in general is that all of the knock rules are marked as constants. And so it makes it very quickly to glance at it and see what's my subject, what's my formula, and what are the operative rules in my formula, because it has the constant markers on there as well. All right, so the first part we need chord to Hoon. Then we're gonna make this real. So that's ream. What is ream doing for us? So you know, make didn't like this, but ream's fine with it. Ream will always turn anything I give it into this. Ream is just wrapping a parser called vast. Delete that part there. So it is simply going to run. Rash is a parser tool. It's going to run text against. Actually, I have vest here. Vest is probably just one of the slightly modified neighbors of Vast. This is one reason why we're going to look at the 2013 version of the compiler in a minute, rather than the current one, because there's a lot of gates that wrap gates. Now, Ream, one of the things about Ream is it's not going to do, it's going to change irregular syntax into things. So you know, I just gave it, let me give it a list here. 1, 2, 3. All right, so what is this sig 1, 2, 3 become? It becomes a col sig, and then it has the values 1, 2, and 3. And it doesn't explicitly represent the sig yet, because this is implied by the col sig that's at the head of it here. Has anyone looked at constants before, like sand versus rock?
It's a bit odd that like both of them like take nouns. And I think with like basically it'll when it read like if it's a noun, it'll put like the aura as like whatever like aura you specified. So you need a bunch of atoms or a bunch of like, I don't know, hex atoms or something. It'll give you that. But it's, I think
Are
it's
you
just,
talking about mint and ride, or make and ride?
no,
Or-
just sand and rock.
Oh, just sand and rock. Oh, yeah. Because we have these parts, you mean?
Yeah, I mean, it's weird that it takes a noun. Like, it'll basically just distribute the aura to all of the nouns inside, I think.
Yeah, and actually, I guess we could like construct I wonder what would happen if we did something weird like that and then tried to let's see, I guess if we reamed it, then we need to open app it to get it to the next step. Yeah, it doesn't care there. So I don't know. I don't know how distributivity and stuff works with the nouns that you run into in that. Anyway, two points I was going to make here. One is that the whole idea of a constant, whether that is a term or some other kind of constant, is basically determined here at the level of Hoon's AST, right? Like knock doesn't know if something's a constant or not. Like to knock, everything's a constant in a way, right? Like it has a value, it receives value. But this is the Hoon type system is being included in this metadata inside of the AST as it runs things. The other point I wanted to make here is that building something in different ways results in different ASTs. So my first one, I did a sig cell 123 ser, and I got a col sig. And in this one, I did cell 123 sig ser, and I got a col tar with a null terminated bust at the end there, right? And actually, now I'm curious what would happen if I marked that as a constant. Comes in as a rock instead of a bust. Okay, I don't know what the difference is there. And so this doesn't vast as the actual Hoon parser is simply saying, take my Hoon, turn it into an AST. It has done no desugaring. It has done no processing, no consideration. It is just a super dumb, straightforward map from one to the other. You can also use the Vang wrapper, which will let you turn off debugging info or dot chords or things. So I had rash text vest here. So if I give it a text, and then I use a particular parser like Vang, I called it a wrapper gate for vast a minute ago. And so what it does is you actually give it a marker for, I think the first one's debugging. Second one's some sort of context path, but I've only ever seen it used as fast, so I'm not actually sure if it's carrying information right now. And if I turn the debugging and dot chords on, then I get, more information about what's happening here, laced into this. So by default, it's in some setting, and you can do things like turn dot chords on or off, and it affects the speed of compilation different ways. But this is all kernel space. We can't really do this directly. Like we can't change the parser and the compiler that's being used from user space unless we're just doing one-off things like what I'm doing here. Once I have a Hoon AST, all right, so I have my Hoon AST. So this is a send call of a wing add. Right, so this is this saying this is the same as give me add and give me 1, 2. It should be, or send call. Sorry, send call add 1, 2. All right, so it is handling irregular syntax, but it's not desugaring things. So the next step is to run it through OpenAP. So if I run it through OpenAP, this is going to unwrap my sugaring one layer at a time. So it's going to do a single pass through and say, can I desugar a send call? And it turns out I can. I can desugar it to a send sig. So it does that. It's pulling the buck arm inside of add, and so this is equivalent to send sig buck add. I don't know, maybe this is like a 1, 2 or something. Oh, that's a list actually. Okay, that's right. Maybe. Interesting. It doesn't actually have a like a col hep or anything implied there. It's just baked in. Anyway, okay. So that's what a send sig gets you. And we can run this multiple times. And so what OpenAP is doing is it's just, and we'll look at the function for OpenAP in a minute too, is every time through it just does a pass and it says, can I change something? Can I update something? So then it changes this to a send tar instead of a send sig. And it presumably makes some other changes here in my values and the way I'm looking at my values. And then I can do it on top of this again and get yet a different result. Yeah, so now I have a tisless and a sendtiz. And I think if I do this one more time, it'll result like a tisgar. Anyway, like at root, Hoon doesn't have that many runes. Most of the runes are convenience runes that are built up to express these things and make it possible to work with them. So, you know, Ream and these others were pretty straightforward. Vast, and there's Vang as your wrapper gate for everything. Vast is your main parser, and it's a huge core with a lot of different particular parsers inside of it. You know, if you've worked with Hoon parsing much, you'll recognize that it's kind of a domain-specific language that arises here, where it's very specific things that we're getting down into, and it runs through all of these. And so unless you're really interested in parsing, there's not a lot to say about Vast except that it builds your AST. Open, on the other hand, is pretty cool because this is where you start to see how you go from one clause to another. And so what open is going to do is it's going to, you know, accept its value. I guess this is put in as the sample in the AP door. And then it's going to run through, and everywhere it finds, you know, it finds a match. It's just going through this huge whatless, and it'll go through and it'll find a match. Okay, so it hits a wing, and it says, okay, we're going to replace that wing with a sentiz of the value that's in it. So there's a wing. Yeah, so there the wing. Well, this wing still has not been resolved. This wing has resolved to a send, or I guess this stuff is resolved to a sentiz. Anyway, but this is where you actually see what the desugarer looks like. So, you know, bar sig resolves to a ket bar of a bar tiz, which, if you think about it for a second, makes sense. We're changing the variance of a gate by doing that. Bar tar is a tisless of a ket tar of a bar pat. Bar pat was the way we would define a wet door. So it's doing something within a wet door of pulling the value out. Anyway, all of these get layered together, and there aren't actually that many Hoon runes at base because of that. I mean, we just run all the way down into these. Actually, a good one to look at would be kethep. Because what is kethep, right? We use kethep all the time to, you know, change things from one to another. But what is kethep? Kethep is, it's a ketless. Ketless is actually more fundamental than kethep. It's more fundamental in Hoon to say, give me something that matches this example. Well, I guess oh, this is because this is resolving to a pat UD. I guess if I did something like that, I could get around it. Yeah, there we go. Right, that we're actually saying, you know, give me an example of the thing that's the P, that's the head of that AST, and then run it against the tail of it with a ketless instead. Anyway, all of these are here, and so you can go compare these to the docs if you're interested in seeing like how are these things actually built. One of the exercises that I will give you is to implement a rune. And so when you implement a rune, the easiest rune to do is going to be to add, we'll call it a Colhax. And it's just going to be a 5-element a 5-element tuple. Oh, well, that's silly. We already have that information. And so all you have to do is just look at your model for like, okay, what does coalesce and coquette do? And I extend it to be one more thing parsed there. Sarpin says, I wish it wasn't just bar cab that added the virtual arms. Are you referring to when we were looking at the bar pat stuff a minute ago?
Yeah, yeah. Thinking about the sort of chorus there, and
Yeah, here's bar
yeah.
cab.
Yeah, it just like the virtual arms, like the less buck, or sorry, less tar. Just adds the tis tars, but only bar cap does it. Although I've kind of desired it in other cases.
Does bar pat do it?
I don't think so.
Interesting. I've never really done anything with wet doors, so I haven't experimented with it in other contexts. It would be nice to have less tar in other cases too, yeah. On the other hand, there's a whole school of thought that's less tar considered harmful. So I don't expect that we will probably see more in that direction. Well, this gets back to, I think I don't know how strong the consensus is, but there's definitely been discussion among the core devs about stripping Hoon back down to an assembly language, like sort of, can we make Hoon better by simplifying Hoon? And the reason is, we've done everything in Hoon because the kernel's written in Hoon, but because Hoon is the only language we have on Urbit right now. If someone did write a Lua or something else on Urbit, you would probably very quickly see a lot of the user space dev done in that other language. And so, if we go down that road, then we may actually see Hoon get more bare bones in a sense, but better adapted to it instead of trying to span. One of the promises of Urbit from early on was, well, we're going to have a single language that spans the entire stack. But I think there's a good question of like, is it actually good to have a single language that spans the entire stack? Like, is it good for the language? Which is an interesting, I don't know. You can make a case both ways. Okay. Let's see. OpenAP. So yeah, so OpenAP is the desugarer. And once you've run OpenAP over everything and nothing changes anymore, you run it again and again until nothing changes anymore. Now you have an AST that's sort of like a mature AST. And this is what actually gets plugged into the UT core, the UT core. Mint is the main arm. It's going to parse from a Hoon AST into a pair of type and knock. That's what we saw earlier. So this is Hoon to knock. But there are another number of other arms that we need to dig around in to actually see how things behave. So I'm going to give you I'm going to copy this over into the screen here too for you. This is the 2013 version of all of UT, but I think we need to see Mint. So that spans from line 7698 to 8178, I guess. Yeah. Okay. All right. So what Mint is going to do, it takes a pair of type and Hoon. So it takes the subject type, whatever, and it takes the Hoon AST, and it's going to produce a pair of type and knock. And it's going to feature a lot of nice checks. Yeah, so what it's gonna basically what it's gonna do is it's gonna process each fundamental Hoon tag, right? So is it a wing? Is it a Barson? Whatever it has, it's going to simplify this down. So for instance, if I'm defining a Barson, which is a standard gold core, then what it's going to do is it's going to run grow, which is its sort of like the next level parser with gold on, I don't know what sig1 is doing here, on the contents of the Hoon, right? Actually, it's called a twig here. That's old terminology. That takes me back. It's a Hoon. Twig is a Hoon. And so this is what it's going to do. Is it's just running down recursively until it has processed every part of this into Nock and has finally resulted in that value there. Wonder what a ditzy is. .z. This is old. Gosh, this is probably Nock. 2013 would have been Nock 8, I think. 8 Kelvin Nock. So things, that part of the parser would have looked fairly different. Like what you're seeing from like an 11 or a 4 or something is probably somewhat different. I guess this .CAD, this is a scry. So the rune hasn't changed, but that's that's a 12 now instead of an 11. So yeah, things have moved around. It's going to use vase mode internally. I had a good example of that picked out, but now I've changed my line numbering. So let me see real quick what the text was for that. Actually, maybe I had that in Hoon.Hoon. That was line 9861 in Hoon.Hoon. Is it this? I don't think this is the one I was actually looking at. Well, let me just look for a slop. Oh, there's only one slop in here.
I mean, the thing is, I think, is like the only way you can get a sort of constant noun in Hoon.Hoon is using like send hand, which I don't think actually appears anywhere. But it is like useful, like that sort of case with slam earlier, like yeah, I don't see it anywhere. See it being used, but it's a way to just basically take just insert a type and some knock, and then you can use like a send one there. So I don't think it would actually use vases anywhere.
I think Mint doesn't use vases. Ford is the main thing that's going to use vases. I think the line that I was thinking of, and I wrote it down as a vase mode thing, but it's not a vase mode thing. But it is neat. Is where it's doing the arm check, like do 2 cores nest properly? So this is, for instance, if you've ever made a Gall agent and you've changed it, you like made 11 arms or you've made 9 arms or something instead of composing a helper core next to it, then it'll fail here, and that's because it's actually looking at, I expect certain number of arms. I expect a certain behavior here. So first it checks that the arms are correct. Are they missing? Are they extra? And then it checks like, are they the right name, right? Like, do you have the names that have the right, arms with the right name? So, but that's actually not I don't know. I had that down with my vase mode stuff because it's not. Okay, let's see. Then so Mint is going to get us some sort of expression. Let's go back to the terminal. All right, so Ream got me an AST, and then I can run Mint of a noun against this. I could also do Mint dot if I wanted to run my current subject, whatever I want to do with that. And now I can I can dot tar the result of that kind of statement against my current subject. So let me do it through make here, just so I don't fill up the screen with text. Right, so make was giving me like some actual knock statement, and then dot tar is evaluating that against the current subject. I could give it a different subject if I had one. Wonder if it would, yeah. So because it's a one, it's a produced constant. It doesn't actually care what the subject is. It's just producing the same value in any case. Yeah, let's see. Yeah, mint. There's a bunch of others too that are in here, like mole. All right, so mole is one that gets called on it's an assertion for wet gates. And basically what it's doing is it's asserting that every place in the code that calls a wet gate needs to check and make sure that the wet gate, when called with that sample, will result in the same knock as it would called with a different, with a reference sample. So what wet gates are kind of doing is they're letting you elide some of the Hoon type information with the promise that you will still end up with the same knock. Let me ignore this type information, and I'll give you the knock that would still be the equivalent if I run it through a dry gate. Is one way to think about what's going on with wet gate. So mole is an assertion over that. Find is neat. Find is doing the wing resolution. I think this is my, yeah, this is my find. So it functionally what it's doing, this gets buried down in these different functions like fond and stuff. Respond. I don't know if it ever actually labels it with a 0. Functionally, what it does is find is trying, it's going to try a knock 0 first to see if the wing is a leg. And then it's going to try a knock 9 if that fails to do a lookup in a core. So it's also going to need information about core variants. So it'll need to know, like, is it gold, iron, zinc, whatever, to make that happen. So that's what fond is doing, is doing the core information stuff there.
The knock 9 would come later. That'll come like I can send his it'll call ergo, and ergo will do like the find. And it's not until it calls fire does it produce the knock 9.
Yeah, there's fire, which is from fine. Fond, yeah. Anyway, these are all nested together with each other. Yeah, there's our core search. I guess that's where it ends up with the knock 9, is through that somewhere.
I think it's an ergo.
It doesn't explicitly do it here anyway, yeah. But ultimately, like, find is your way into this rabbit's warren of pieces here. This is why I said, if you want to understand the compiler, take a look at the 2013 compiler first, because it has not yet differentiated into functions that call functions that call functions the way that the current Hoon compiler is. There's a reason that the Hoon compiler is not really documented.
There is a sort of Google Drive document that gets floated around.
I'd like to see that sometime. I don't know if I've seen that one or not. Yeah, so slab gives you information about what permissions you have on some particular core. Like, can I read it? Can I write it? Can I do different things inside of it? What's neat about slab, again, from like a dynamic programming perspective, is slab will let you know if you can read or write particular faces in the sample. So like add has an A and a B in the sample. So I do have the ability to write both of those, and then C does not exist. So I can't write to C. There's no C there. And that's going through font too. So it goes back around.
Does that do anything other than just check if like a face exists? Are there like other permissions for cores where you're not actually allowed to write values? I guess this might be a difference between like lead and these other types I'm not super familiar with.
Well, so what slab is doing is saying, can I access a particular arm, right? Can I reach a particular value? There are other ways to extract the information. Like what's an example of what you're proposing to do?
I'm not proposing anything in particular. It was just you were talking about like reads and writes, and I was like, are there permission? Like what I was thinking was like, are there permissions on cores? But it sounds like it's mostly just like, does this face exist within this type or something?
What does this say right here? The fourth case of vial 3 is not permitted because it would allow you to discover private information about a type, information which you could not make use of in law-abiding Hoon anyway. So yeah, if you're willing to go to vase mode or actually look at your AST and stuff, you can do an awful lot of checks on things that you cannot do in conventional Hoon.
Interesting.
But user space is fairly sandboxed in that regard.
I see. All right, thank you.
All right, there's Mint. Let's see, we'll cover Ford and build file stuff. Let's look at what Nock has actually produced. That's worth seeing there. All right, so this is Nock as Hoon conceives of Nock. This is the Hoon perspective on Nock. So it's a whole list of constant tagged formula that you can put together here, plus an autocons rule. Not really any surprises here, but I think it's actually a pretty readable representation, which I like about it. Let's look at Ford then. Let's see. I guess Ford is in Clay. All right, so here's the Ford arm. Okay, so Ford was a vein. Ford's not a vein anymore. What is Ford? Ford is the code builder arm. And what it does is it handles producing code from a file on disk. And what makes it different from something like Ream or Mint is that it has to be able to handle file import. So it has to be able to build multiple files and then compose them together. So it's going to use the slap slop algebra to do this internally. It also has some state. Clay actually has some stateful information to trigger Ford build. So for instance, if you bar commit code that changes, then Gall can subscribe to the next revision of any query that's made to Clay. And this is why if you bar commit to a running agent, that agent will just rebuild automatically because Ford is maintaining this this state about what it knows, which is it's convenient. So with a SIR file, like if you use a whethep, then it's going to build the SIR file, and then it's going to slop that vase with Zeus or your reference library to yield the new build subject, which is going to be a new vase. And then that build subject is what's going to be used when you slap the file. You're going to slap the file contents against that build subject. If I can spell. That's the Mark core stuff. This is. What's diffs? It's going to be in one of these builds buried down here, but after the Mark stuff. Actually, that's a nice demonstration here, right? That when we're actually importing specific types and structures in Clay, it is just explicitly slapping Zeus against the Hoon that comes from building those components in Clay. That's a nice clean design pattern there. So this is what Ford does, and since Ford and Clay resolve across the context of a desk, it means we have some interesting consequences, like I can have two identical Hoon files with imports that result in different knock. Because the imports that I have may be different on the two different desks. I may be importing a library with the same name, but the library may be different versions. And so there's some consequences about this that I know have been debated on. You know, is there a way that we can actually clean this up? Because we don't like the fact that a Hoon code with the same text could resolve to different evaluation now in the end. Let's see, let's look at, so build file thread is one that you've probably used. It doesn't do a lot. It passes it through Strand.io. So Strand.io is actually going to handle the build file operation right there. So, you know, it pulls it up, but then it kicks it right over. So if we go to lib Strand.io, we can see what's going on there. All right, so this build file is taking a ship, a desk, and a case, and a spur. What's a spur? I don't remember what a spur is. Spur must be a general type from Clay.
I think it's
a
like
path. It's a path. It's a path.
yeah.
Oh, that's right. That's right. The spur is the path after the beak.
No, I think it includes the beak.
Well,
Although
this
maybe,
is.
oh yeah, no, maybe not. Yeah, never mind. I think there's a spar or something. I forget. Like I remember.
Yeah,
seeing
there's some
notes where like they actually hard code like the ship, desk, and case into the path.
Yeah.
And I thought that was called a spur, but maybe it was called like spar or something.
Mm-hmm. Yeah, so this is building source files at a particular place. So it's loading this this warp stuff from Clay, pulling this value in, and then if I think the riot stuff is, if I recall correctly, Mark checks, and then ultimately what it does is it runs it through, makes sure that it's a vase, and then produces the result of collapsing that back down to a pair of, you know, type and we want to resolve it back into the static context. It's like whatever the result of a build file is, which, as it turns out, is a vase. Like when we build a file, we get a vase, and then we can use that file whenever we're going to use it as a library. We're resolving things within that vase, and Dojo and so forth handles this fluidly for us. So it's kind of neat to see how this starts to work. Next time, we're going to get more into marks and tubes and how that layer of the transformation works. And then when we get to Clay in a few weeks, we'll really get deep into that. I'm going to go ahead and skip there's a Rune AST tutorial that I will give you, and you should walk through it to understand how to actually modify a rune. It just walks you through, like, here's the entire life cycle of a rune, and it's Barbuck, which is used to build a mold builder gate. So, you know, how do you find where it's specified in the AST. What does it convert to an open AP? What is it, just can we walk through that whole process, nose to tail? All right. So to wrap up, let's talk a little bit about Hoon and Nock 9. Okay, so if Hoon is an assembly language macro for Nock as a machine code, which I think there's a stronger case for this even after you've seen what you've seen today. One of the most common patterns in Hoon is how a gate is defined as a core and then invoked into a particular instance by replacing the sample and then evaluating the statement. So for instance, if I were to zap tis senhep add 3-4, just some invocation like this, what I get is a Nock statement that has 2 Nock 9 pulls embedded in it. So functionally what happens is it takes the add core, it modifies its sample to be constant 3-4. That's what's happening here. And then it fires the buck arm, which is going to be at axis 2. That's the battery. So this 936 stuff is what's actually getting the add arm of that. We're getting the add arm from the parent core. So you can connect how Nock is thinking of this double Nock 9 to how Hoon has a hold, and then how it resolves it into a core. To loop back to what we were running into with type stuff at the beginning. So if we're actually going to look at into add, where we can get the hold, then we can kind of resolve it down. Let's see if we can do this. So if I get the left-hand side, the head of add, then it should give me the type of type. Okay, so no surprises there. If I get, what's it, axis 4 in there, then I get the hold out. I could keep going deeper and grab other things, like there's my sigfaz, that's my dot chord stuff, and go farther down through there. But what I'd actually like to do then is resolve this. Let me see if, let me do tar add. All right, so tar add by itself results in 0. But if I zap gal tar add, let's see, this was working for me earlier. Yeah, I can get down inside of what it thinks tar add is and ask it particular questions about what it sees. Actually, now that I say that, I'm not actually sure if that's what I'm doing. I think I'm actually looking inside of at when I wrote that example. That's fun. It's always fun to write an example and realize that it's not doing what you thought it was doing. I'm looking inside of at because tar add is already resolving to particular value there. Let's do this another way. Let's go back to mint to show you what I want to show you here. Okay, so if I have a core, okay, so if I want to run something from mint, I need to invoke mint against some type, right? So I could invoke it against the current subject. And then noun, and then I could ream it, or I could zap comment with tar Hoon, whatever I want to do. Get this value here. So if I give it a core, well, let's do that. Let's give it a core instead of a I think that needs to be the type. Yeah, the problem is that the error with the need have actually looks a lot like the correct answer. Okay. All right, so what's happening here? This is another way of showing you kind of what's going on with those. So the way I was getting into this, I was talking about how your double knock 9 in knock is analogous to the way that we retrieve a core, we replace the sample, and then we run that core. And so what I wanted to show you here is what's happening when Mint produces knock from some particular value. Mint is returning a 3 tuple here to us. The head of this tuple is the battery of the core. Which has a lot of stuff in it. Then the tail of it is so we have a knock 8 with a couple values here. Okay, so what we have is the middle of this is the default sample of the core, which is going to be the zeros that get produced by this. So there's a 1 0, for instance, is getting produced here. So let me put it this way. Mint UT returns a 3 tuple. The head is the battery of core. This is the bunted sample, or knock 1 of bunted sample. And then the tail is subject. All right. So that's what this piece at the end is doing here. And so what happens is we compile the core, we get the core back. We have the core, which has the battery, it has the default sample, and it has the context. So this is your battery sample payload, or your battery sample context layout here, battery sample context with the default sample. And then when you 0 1 in, you pull in your current subject. At the same time, it's going to do a replacement of the default, the default bunted sample with the arguments that you're giving when you invoke that core at that point. And what I like about this is it shows you where battery sample context come from in knock terms, that we actually have like a bunch of knock, then we have the bunt of the sample, and then we have a 0 1, and then the bunt is going to be like knock 1 of whatever. Like this arises naturally. I don't know what order these things were come up with in, but this arises naturally out of the context, out of the situation in which we are compiling things into knock, and these are why the pieces of knock come in the order that we get them here. Knock is not Mint as an ARM isn't really doing anything special to optimize. It will replace some simple expressions, like if you have a knock 7 of 2 knock 0s, it'll turn that into a single knock 0, for instance. But for the most part, it has not been a design goal of Urbit to produce an optimizing knock compiler under the philosophy that should be resolved at the level of producing knock bytecode, which is a runtime operation. And it's sometimes, if we run an X-ray hint or whatever, it's visible from Arvo, but it's not run in Arvo. So that's a thing to keep in mind as you take a look at Mint and everything, that it's reflecting the higher order principles that you've run into earlier in your Hoon education as you've gotten used to this. Now, the exercises that we're going to come up with coming out of this, I'll send you these, but The first one's going to be writing your own slam. We did a version of that earlier. So you can look at that, think through it, think about like what would be an elegant way to express it. Writing slam using slap and slop is not, conceptually, it's not hard. Trying to figure out how to embody it in code can be a little bit of a pain sometimes, but that's part of the exercise. And then the other exercise is going to be implementing a rune. So we're going to make a 5-tuple rune. So it should follow the same pattern as Col Hep, Colas, Colcat. You'll probably have to change, I think, 3 places in the code. You'll have to make sure that it can get parsed, that Colhax has a place to parse. You'll have to make sure that it has a place in OpenAP to resolve down to the actually maybe just 2 places. Come to think of it, because I think you'll just need to modify OpenAP and then have a parser that actually picks up Colhax and produces like a send CLHX value for you there. So I think both of those should feel moderately straightforward for you to do, and go from there. Questions?
Something that I find in the parser that I find is funny is there's like the expa blah 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 blah. It ends at Z, so I've always like wondered like what when we add another one, what do we call it? Those are like the things that'll like parse like as like the parser has these things where it's like, oh, you have a rune and like this is like the symbol for the rune, like send TSLS or something.
Mhm.
And then like the sort of NRE sort of arguments. Seems to be like exactly 26. And they're labeled like EXPA, XPB. I don't know what to call
Yeah,
them.
that are doing yeah, you're talking about these.
Yeah.
Well, K and L are currently abandoned. So, there's some room to squat in the middle here, I suppose. I mean, maybe we change, I guess the Qs are already taken here,
I think maybe just the next one's like EXP0, I guess.
maybe. Buys you 10 more anyway. All right. So that is how Hoon gets to knock ultimately.